Hi, my name's Glenn Weinreb, and today we're going to talk about how our society might tackle the climate problem with a new R&D laboratory. And this is part 12 of our Climate Solution video series. We begin with a question. If a new R&D laboratory was set up, what might it do that is not already being done and has the potential for significant impact? We will explore this question in this video. Also, we put together a business plan for a new R&D lab, and this can be read for free at the address shown here. Before we begin, let's review the problem. There are multiple components to global warming, each of which are shown here. Some components increase global warming, whereas others decrease global warming. These combine to get total warming, which is the same as observed warming. One of the components is global cooling, which is caused by sunlight reflecting off of particles and droplets in the atmosphere. In some cases, this is caused by air pollution. What is fascinating about this component is the error bars. These tell us that climate scientists do not know if this is a little or a lot. Unfortunately, the difference between these two is profound. If planet cooling is large, then climate models say significant changes will occur to our planet over the next 30 years. Otherwise, if planet cooling is small, climate models tell us changes will occur more slowly. IPCC reports that appear on the desks of national leaders are based on models that assume cooling is moderate and changes will occur more slowly. However, these models are not consistent with actual measurements. For example, satellites measure global warming in the atmosphere versus time, as shown here, and they see one blanket around the planet due to 150 years of carbon dioxide and methane, and they see a second blanket of comparable size appear over the last 10 years. This second blanket is not explained by carbon dioxide, methane, or tipping points. I know this sounds crazy, yet this is seen by satellites, and this was the focus of the most important climate paper published in 2023. The author was the director of the NASA Goddard Institute for Space Studies for 32 years and is considered to be one of the world's top climate scientists. According to him, the leading explanation for this second blanket is the world reduced air pollution starting about 10 years ago, and this caused less sunlight to reflect back into outer space. In other words, less air pollution leads to less reflected sunlight, which leads to less cooling and more warming. It turns out that reflecting just 1/400th of sunlight has a big impact. Our society filters out air pollution because it is not healthy. This is typically achieved by filtering out pollutants at a refinery before or after the combustion of fossil fuel. Now, back to our second blanket. This is also seen by global temperature measurements. More specifically, global temperature increased 0.18 degrees Celsius between 1970 and 2010, and this rate seems to have increased 50 to 100% over the last 10 years. In other words, global warming is accelerating due to less air pollution and tipping points. And the climate problem has probably been understated by climate scientists because they do not know the value of one parameter. I understand the climate problem sounds terrible. However, it can be resolved with minimal disruption, as we will explain in this video. We primarily have two climate problems. One is global warming from carbon dioxide, and the other is global warming from tipping points. We can resolve the carbon dioxide problem by replacing coal, oil, and gas with solar, wind, hydro, and nuclear. However, this will not solve the tipping point problem. We seem to be tipping too fast. Therefore, we probably need to reflect a tiny percentage of sunlight back into outer space. The reflected amount would be so small, people would barely notice. There are several ways to do this, one of which is to inject sulfur into the atmosphere above where airplanes typically fly. Sulfur is contained within coal and oil and is therefore commonly emitted upon combustion. In theory, we can filter it out before combustion, move the harvested sulfur to an airplane, and emit it at a high altitude instead of a low altitude. High altitude sulfur stays aloft for a year or two, while low altitude sulfur typically stays aloft for several days. Therefore, changing the emission site reduces the temperature of the planet while not increasing total sulfur emissions. The latter point is important since sulfur is harmful to people, plants, and oceans. In other words, it is not healthy to stand next to this thing. To justify the expense, our society would need to compare the cost of cooling the planet with the cost of not cooling the planet. One study suggests large-scale planet cooling would cost $18 billion a year. For comparison, the total value of New York City property is $1,300 billion. And this is just one coastal city that would be lost to sea level rise. Now let's look at how a new R&D lab might tackle the climate problem. And let's begin by reviewing our original question. If a new lab was set up, what might it do that is not already being done? We will touch on a few ideas in this video, and for details, see the free document mentioned previously. In order to survive climate change, the public needs to understand the problem and the solution. And to communicate this, the proposed lab maintains a planet dashboard. This would be a website that explains what is expected to happen to the planet each year over the next 100 years. It does this with graphs that show expected global temperature increase, sea level rise, food production decrease, amount of money lost due to global warming, and planet cooling needed to block an insane sequence of events. In other words, the planet problem is summarized with several graphs. Also, the user could drill down and see components that make up each graph. For example, global temperature increase is the sum of temperature increase from carbon dioxide plus temperature increase from melting sea ice plus temperature increase from thawing permafrost. Component graphs are helpful because they would illustrate what is expected to happen, when, where, and to what extent. And this would help the public understand the expected sequence of events. Each event is typically associated with a tipping point, several of which are summarized here. These are activated by heat, and after being activated, they create more heat. In other words, they activate each other and are therefore like dominoes. For example, melting North Pole sea ice is expected to cause snow on Greenland to melt, which will reduce ocean currents, which will decrease moisture in soil, which will reduce food production. More specifically, a recent study predicts the amount of global land suitable for growing corn and wheat to decrease twofold by the year 2055. That statement might sound crazy, however, we are already observing less water. This begs an important question. How much does it cost to block the first tipping point? The Planet Dashboard calculates this and plots this cost as a function of time. And this enables the website user to compare the cost of cooling the planet with the cost of not cooling the planet. the website's graphs are generated by climate models. These are confusing. Therefore, they are selected by top scientists, and the website user selects a scientist, not a model. For example, one website user might trust the leader of the IPCC, while another user trusts the leader of NOAA. The website user must also specify how many years they expect our society to emit carbon dioxide. Many economists expect this to be over 100 years, while climate activists prefer less than 40 years. After the user selects a climate scientist and a decarbonization profile, the graphs appear. These are important since they help the public understand the climate problem. And they illustrate how, when, and why we might block tipping points. In theory, we can solve the carbon dioxide problem by reducing carbon dioxide emissions. However, we were already doing this, kind of, and global carbon dioxide emissions are increasing, not decreasing. We are failing because we ignore basic principles of economics, government, science, and engineering. If we instead adhered to principles, fixing climate would be much easier. For details on what this entails, see Climate Solution video number 11. It is unlikely that lawmakers would support major changes to their economy without a detailed climate plan. These plans do not exist. However, they could be generated with a little software and existing economic models. The proposed lab remedies this with a website that creates a climate plan after the user specifies a strategy. For example, the website user might want to decarbonize nation Z over X years at lowest cost, in lowest cost order, with additional costs passed on to consumers. The website would then produce a climate plan, which would be a list of initiatives that are implemented each year over the next few decades. For each initiative, the following would be estimated: cost, carbon dioxide reduced, and cost per ton of carbon dioxide reduced. This might seem like artificial intelligence. However, economists have methods for producing this information without AI. The lab's climate plan website would support multiple nations since everyone needs to decarbonize, not just one nation. For more information, see Climate Solution video number 8. The previously discussed website would answer the following question: how much does it cost to fix the climate problem? An example answer is shown in this table. All numbers are in units of dollars cost per American per year. Europeans would see similar numbers. These costs would show up as an increase in the cost of goods and services, in addition to money spent by government. Costs are divided into 3 categories: planet cooling, additional cost for green products, and more R&D. This table assumes decarbonization occurs over 30 years at a constant rate, and it assumes decarbonization green premium costs start out at $20 per ton of carbon dioxide reduced and increase over 30 years to $80 per ton. The left part of the table looks at years 1, 2, and 3, while the right part of the table looks at years 10, 20, and 30. One might think of these as the early years and the later years. The early years are relatively easy since green premium costs are proportional to the amount of carbon dioxide reduced, and initially this is small. For details on this table, see Climate Solution video number 11. Increasing atmospheric reflectivity is a new field, and there are many things we do not know. We do not know what to inject, when, where, and how, and we do not have an accurate assessment of costs and potential side effects. To resolve unknowns, the proposed lab does R&D. This includes developing better instrumentation for measuring atmospheric reflectivity, developing equipment that injects small amounts of material for field experiments, and developing equipment that injects large amounts of material for full-scale operations. Scientists are currently studying how to generate energy with a hot plasma inside a donut-shaped structure. This is referred to as tokamak fusion, and some scientists believe it will not be commercially available for another 20 years. However, a billion-dollar-sized R&D initiative, overseen by the world's top scientists, could potentially get this done sooner. For details, see the fusion chapter in our business plan. Nuclear fission is the traditional form of nuclear power, and it is not popular due to 4 reasons: meltdown risk, nuclear waste, nuclear bomb proliferation risk, and high cost. In theory, these areas could be improved to the satisfaction of the public. For details, see our fission chapter. In theory, we could develop next-generation buildings where each device in the building has a processor that can reliably communicate with all other devices and with the utility company. Devices include appliances, heating and air conditioning equipment, lights, motorized dampers and vents, temperature sensors, occupancy sensors, motorized thermal covers for windows, etc. This would enable the building to reduce energy consumption via multiple techniques. For details, see our building automation chapter. In 1940, MIT President Carl Compton mobilized his resources to tackle the war problem in Europe. More specifically, he set up a laboratory to develop radar and other microwave technology. Some people credit this with helping to win World War II. Fast forward to today, 84 years later, and we have MIT President Sally Kornbluth exploring how to mobilize her resources to save the world from climate change. Like her predecessor, this involves identifying projects which are currently not being done and have the potential for significant impact. Decisions about what to work on and how to approach each project are of profound importance, and we wish her Godspeed in these efforts. For more climate solution videos, visit the link shown here. Thank you for listening.